we have Timo Bremer, who shares an appointment at Livermore, Lawrence Livermore National Laboratories Center for Applied Scientific Computing, focusing on large-scale data analysis and visualization, and at the University of Utah, serving as Associate Director for Research of the Center for Extreme Data Management Analysis and Visualization. His research interests include large-scale machine learning, data analysis, visualization, medical image analysis, topology, volume modeling, and virtual reality. And we would really like to thank Timo for this last-minute availability to give a talk at the school. Thank you, Timo. Go ahead.
Absolutely. No, thanks for inviting me. This is always fun. Yeah, so since this was kind of last minute, we're gonna jump through two related presentations that I think are gonna be hopefully interesting. But because this wasn't originally intended for this audience, feel free to jump in and ask any questions, because I know that I can always explain stuff better, and hopefully we can all learn something in the process. So what we've been doing a lot initially was just data analysis. And what I'm going to show today is a bunch of recent work that we've done to better understand high-dimensional data, in particular in the context of like optimization or even machine learning on general data analysis. So we're going to go into that. Not there, here. So in general, right, understanding high-dimensional data is very important in a number of applications, right? Whether I have a physics ensemble of computation where I've got inputs of the physics code and then write the yield of the implosion or something like that, I might want to compare different ensembles. I might want to understand, right, where my local maxima minima are. I might go to material science and understand equations of states, right, where I've got so many inputs and the pressure of the material. I might have climate ensembles. I have generically kind of man-made systems, right? So the energy grid or communication networks, even analysis. A lot of times I can express that as, right, a bunch of independent parameters with some dependent values. Now, on my side, right, once you decouple that from the application, you can really just think of this as the very general challenge of understanding relationships in high-dimensional multivariate data. So that typically just comes in literally at the table, like you've got an Excel table where every row is one experiment or one simulation or generically like one database entry, right? And every column is some attribute of interest that you have. And now you more or less kind of not randomly, but very flexibly, you can essentially do this mental exercise and call some of your columns to be independent, right? Input parameters. And that makes all of the other columns kind of dependent. And now you're thinking about, okay, so I really would like to understand what this function is, right? What is this f that gets me from the independent to the dependent? How could I model that? And obviously, right, I can choose my different x's, right? Tomorrow, I could choose different columns. I can choose different y's. I can choose different x's. But generically, I want to understand, okay, what is that function? Where is the maxima? How complex is that function, right? So it turns out that if you look at that kind of abstractly, more or less every tool out there follows a very well-established paradigm. So you get a bunch of input data, right, these rows, and you treat every row as a high-dimensional point. So you just take every independent variable, you treat it as a coordinate, and so you've got a bunch of points embedded in high-dimensional space, and we're gonna think of that as kind of the domain of your function, right? We've got a domain that's x, and we've got a range that's y. But of course, the individual points don't really help you, right? Because they're just individual measurements. They don't help you much. So instead, we typically need to create some sort of graph that connects the points. And for you guys with a lot of physics background, this is really, you need to approximate the intrinsic space from which you sampled that space. So the graph essentially makes your independent set of points into some sort of manifold structure, right? That actually describes your space. So it gives you some sort of continuity, and it's necessary for you to talk about things like gradients or interpolations. So you have to make that graph, and then ultimately you select in this talk here, we're always going to do a single scalar value. Everything else gets even more complicated. So you select a property of interest, and you think of that as the range of your functions. Or, right, the way I've tried to draw that here, you think of those as kind of function values on the nodes of your graph, right? So you've got this augmented graph that really describes the high dimensional functions, right? Every vertex has a single function value, and then you've got this embedded terrain that you have. And then you try to kind of visualize or explore or analyze in some way, shape, or form how this function changes, right? You can make a colored scatter plot, you can do a whole bunch of other stuff. Okay, so that's kind of what we're trying to solve. So it turns out that there's a whole number of techniques in which we can do, but one paradigm that we've used is topological analysis. And the reason we came to that is that topology has proven very successfully kind of a low-dimensional analysis where we're just trying to understand, right, three-dimensional structures. You see here a couple examples, right? The left is a Rayleigh-Taylor instability. The right is some porous material under impact. The bottom ones are combustion simulations, where we have various notions of what we consider a feature that we want to extract. We might want to know how large they are. And topological techniques, kind of understanding the maxima and minima and saddle points and so on of a scalar field, have turned out to be very, very useful to make kind of generic tools to extract not just one particular type of features, but many different features in kind of a almost like a different language, right? I can describe many different scalar features as part of some topological construct. And as long as I have a piece of code, which we do, to extract like the topology as a whole, I can always extract kind of a wide variety of features as subsets of that overall topology. So topology produces a whole bunch of things like graphs and trees that turns out to perfectly generalize to high dimensions, other than many other analysis techniques, right? So the underlying theory of topology, and I'm going to show some examples later on of what we mean by topology in this particular instance, but the theory is long known and is defined in arbitrary dimensions, right? People talk about infinite dimensional spaces and stuff. We actually have algorithms that enable us to compute topological structures such as merge trees and Morse complexes and contour trees in arbitrary dimensions. They're approximate, but they work pretty well. And what we get out are these abstract representations of kind of properties of our functions, where we get concepts like what's called a merge tree, which are connected component superlet structures. So these are just threshold-based segmentations. So if you want to know, right, what are all the ranges in my functions with like value above X, then constructing a merge tree actually tells you that, right? There's things like Morse complexes, which are segmentations according to maxima, which is actually what we're going to use here. There's a more complex version of Morse-Mer complex. But generically, these are very useful because they encode kind of a very difficult to understand high-dimensional information into much more abstract, lower-dimensional concepts that we can then actually use to develop new visual metaphors. And that's kind of part of what I'm going to show here in the talk. So let's look at how that actually works. So we're going to use a concept that's called the Morse complex. And this is kind of a two-dimensional example. So imagine you have a two-dimensional terrain. What you can do is you can essentially take a ball and kind of take your virtual ball and let it roll on that terrain. And you figure out kind of which minima it rolls to. And then you color your terrain essentially by, right, by which minimum does that ball roll into, and you get what's called the unstable manifolds of this function. So I've got this color, right? So you divide everything into these valleys. They're separated by ridges, right? The valley, each valley has a local minimum on its bottom, and it's got a bunch of saddles and maxes kind of on the boundary. Of course, I can do the opposite, right? I can do the stable manifolds, so-called, right? So I can color everything based on, right, the maximum that I flow to. So why would I care? Because, right, one of the things you can do now with the structure is you can talk about kind of a topological-based simplification, where you're saying, well, some of these mountains are more important than others, right? So some of you might have noticed, for example, there's this guy over here, where you can see my mouse, right, where just for sampling artifacts, you have two maxes that are almost the same, right? There are two, oh, thank you, Docker, for that update. Right, it really should be one mountain, but just for sampling artifacts, it ended up with two. So right, it's kind of unimportant. So there's this notion of, well, some mountains should really be merged, while others kind of, right, this guy is very stable. So you've got this notion of topological simplification, where what we actually do is, instead of doing things like size or explicit function value, we actually look at the relative distance. So the relative function values between the saddle point and the maximum, the lower maximum. That's a value that's called the persistence of this mountain. And essentially it encodes something like, by how much do I have to flatten the little mountain until it no longer becomes a maximum, right? What's the minimal change in function value I have to do for this little mountain to disappear? And right, as you can probably note, right, it's the function value. I can push this guy down to the function value of the saddle, at which point both of them disappear. And I essentially, at least conceptually, get the structure on the right where I only have one mountain anymore. And we can do this, right? So we can take all the maximum that we saw before, and we can do the simplification. And under some persistence, right, we saw that like the guy over here, that's really just all one ridge, right? A bunch of other, like this guy also merged just for simplification. So I've got a notion of not just what are the local maximum, but I also have a notion of stability, right? How large are they? How significant are they? And kind of in terms of, if these were like experimental data, you would say, for example, right, every mountain that is below my error threshold in my inputs, right, is meaningless, because right, that's just random noise, because I'm not sure that information is actually real. So then I clearly want to simplify everything like below the noise threshold. So topology actually can provide a very intuitive notion then to understand high dimensional dependencies as functions. So this traditionally we do what you're probably familiar with if in high dimensional visualization is you first project the data, let's say in a two-dimensional scatter plot or some dimension reduction or a TSNE plot. And then you try to look at that projection, essentially you try to analyze it and try to make sense out of it. But the problem is that initial projection could have destroyed a lot of the data that you're looking for. And so now you're dealing with projection artifacts and stuff. Here we do the opposite, right? We're saying, why don't we analyze the function in high dimensions using topology because it happens to scale? And then we're going to figure out some visual encoding, some reduction later to actually show you what you want to show. That is helped by this notion of hierarchical feature definition. So we can do this at different scales. We also get these, right? I showed a bunch of colors, right, as stable manifolds, and this was just initially for presentation purposes. But of course, these colors also represent the fact that we actually have a segmentation into coherent regions. So not only do we know where the local max is, but we actually know what's the mountain kind of surrounding that max, right? What is the region that really kind of conceptually belongs to that maximum? That turns out to be very useful for localized analysis, as we're going to see. And then also the abstract graphs can actually give you better visual encodings. And because we haven't done anything specific, right, I can do this with any data set that I want. So let's look at an example that might actually be more familiar to some people. So this is some by now really old simulation data from the National Ignition Campaign, one of the first things that we got from them, where they were interested, right, in analyzing the yield of the implosion at the NIF. Right, so they do all kinds of simulations. This happens to be an ensemble of 1D simulations of the NIF implosion. And so here I show you one of the standard scatter plots that they might use, right? The x-axis is downscatter ratio. Don't ask me exactly what that is because I'm not physics trained, but some important input parameters about the capsule. And the y parameter here is the actual final yield of what you got from the implosion. And this actually comes from a 5-dimensional simulation, meaning they had 5 different input parameters that they were varying, and they were looking at how yield would change under those input parameters. Okay. I would say that if I were to look at the scatter plot in this way, it doesn't really tell me anything, right? I mean, yeah, there seems to be, right? There seems to be one range in the middle where there's a high yield, but other than that, I don't see any strong dependency on the downscatter ratio at all. But if you actually go into the high dimensional space, so you take the 5-dimensional input space, you do the topological decomposition there, it turns out that you actually find 2 mountains. You find two very well separated regions of high yield. And then I can take the same scatter plot and I simply color it by the two different mountains. So there's a black mountain, there's a red mountain, and there's a blue mountain. They both kind of get fairly high yields. And again, here it's not quite obvious, but if I like separate them out, it turns out that the blue one actually has a pretty, like for this type of data anyway, a pretty strong dependency on the downscatter ratio. So there is a region in parameter space that actually has a fairly pronounced dependency on the downscatter ratio that otherwise wasn't obvious at all, right? And also it means that the red mountain, so there's the red region that gives you a high yield, which doesn't depend on downscatter ratio. And then there's the blue region in parameter space that actually does. So maybe there's two different physics going on, right? I don't know. Maybe there's a different process that actually happens to make that yield high, right? But that's information that would have been very, very difficult to get just looking at the scatter plot alone. We look at another example, right? This is something similar. These actually are 2D simulations, 2D higher simulations in 6-dimensional input space. And these are two of the initial inputs, the burn width of the capsule and the total entropy. Again, looking at the scatter plot, I would dare anybody to actually see any kind of really meaningful structure in there. But if you do the same trick, go in a 6D input space, compute the topology of yield as, right, where are the high values of yield? Turns out you find 3 different local maxima of yield that are very well separated. And again, if you do the same trick, right, you color this by yield, all of a sudden, a lot of structure appears. So if you look at these 3 things, you'll find that there's one big region where you can get a high yield that has essentially no dependency between burn width and entropy, which actually is kind of weird, I've been told, because you expect those 2 things to be related, because the wider the larger the entropy is, that the wider the burn width will be. So you would expect there to be a relationship, but it doesn't exist. But then the other ones actually have a strong relationship between burn width and entropy, as you would expect. So again, just the simple colored scatter plot actually helps you understand this in a way that would have been very, very difficult for you to otherwise figure out, because right in the projection, it's not apparent at all anymore that there are regions of high yield. But if you do the topological analysis first and then do the color afterwards, it actually does help you to understand this. But of course, by coloring the scatter plot just like this, it's kind of crude, right? It's kind of limited to in its way, right? I still can only see 2 dimensions. It doesn't really show me high dimensional space. So is there something that we can do better, right? Can we look at the function directly? And it turns out that we potentially actually can. So remember this picture, right? So we have this notion of what maximum can cancel into another one. That's the topological language, right? So if I remove this, the way the topologists think of this is, right, that this maximum gets canceled into that maximum. And another way of thinking about it is actually that this operation, by saying that these guys cancel, you are kind of saying that this mountain ridge is important. So in 2D, it's actually fairly intuitive, and I can explain it in high dimensions, but in 2 dimensions, it's easier, right? So here, every saddle point, you kind of have the mental option. You can think of this as the ridge between 2 mountains, or you can think about this guy as kind of the path between 2 minimas. Well, actually, no, sorry, it's the opposite, right? It's the ridge between 2 minimas or the path between 2 mountains. And it's kind of contextual, like which is which, right? If this is, in this case, it's really high. So this is a separation between the minima. This is a ridge. Versus, right, this guy over here is very low. And we will probably just say, well, that's just a path, right? That separates, like, this max from some other arbitrary max that lives here. But that actually tells us that some of these connections are important ridges and others are not. And we can use this to actually just extract all important ridges, and we get a structure that looks kind of like this. So this is kind of the similar terrain, but now you're looking straight down, and this is a contour plot, just like you would get from like a topographical map. So we've got all these maxes, and if I look at how these maxes would cancel, if I were to simplify them, and I just look at the stuff that gets canceled over, I get what we like wittingly called the cancellation tree. And what the cancellation tree actually is, it's a collection of the really important ridges in your data that connect your local maxes. So it tells you kind of the structure of where all the maxes are and how they're connected, right? How many neighbors do they have? But because it's maxes and saddles, I still have the function values. So what I can now do is I can actually, instead of looking at this kind of embedded, I can look at the abstract structure, right? I can just look at the graph. Why do I want to do that? Well, because the graph is actually, I can compute this graph in arbitrary dimensions, but of course the left plot I can only make in 2D. So I can compute the graph in high dimensions and plot kind of just the abstract graph. But what I still have is I still have the function values. So can I kind of create something similar to this plot? And it turns out I can, right? I can think about as generic, let's look at the total generic structure, right? I've got two maxes separated by a saddle. Because I know their function value, I know how their contour values, right? How the height values are nested, right? If I tell you that this is 10 and this is 8 and that saddle is at 7, you know what the structure looks like, right? It looks exactly like this. It's like so I can make a canonical contour plot for this pair, right? I know that there's a contour that is alone around this max. There's another contour that's alone. There must be a contour at the saddle that makes this well-known figure 8, right? Then there's something right below the saddle that makes up kind of this connected figure 8. And I can even look at things like, I know how many points are in this mountain, so I can make it as big as kind of relative to the volume it actually takes in high dimensional space. I can make this guy as big as I need. So I can actually create, I can create another terrain that has the same topological structure as my high dimensional function, but now it's an actual 2-dimensional terrain, right? So this is an example from just 3D to 2D. So this just happens to be the temperature inside. This is a combustion chamber. And right, this is a fairly high quality volume rendering, and still I would maintain that it's kind of sort of hard to understand exactly what the structure is of right temperature in this chamber. This is the corresponding what we call topological spine, right? So I did the same thing. I extracted all the high value of temperatures. I connected them by their most important saddle. And then I just computed, right? I just made this arbitrary topography out of it because I happen to know the function value. So I know how they're nested. I know how large they are. And I get this very nice kind of, I would contain very nice abstract structure that tells me exactly what this thing is doing. And it's much easier for me to look at, right? I would contain that this image below, the 2D plot on a conceptual basis, it's much easier to understand than the 3D structure, even though, of course, the 3D structure, at least I could look at, but I could do this now in arbitrary dimensions. So here, for example, I mean, one thing that I really like is that this just naturally creates this kind of almost Egyptian thing, right? Where in 3D space, this line and the ring around it, right, is orthogonally oriented. But in 2D, right, they just get flattened out, just like the Egyptians showed you, right, the front of the body and then the head on the side as well. So, and I can understand these things where I know that these local maxima, where they are and how they're nested. I could do that with some effort in the 3D volume rendering as well, but it would be much harder, right? And just kind of for demonstration purposes, let's look at just a chemical element, right? Cyclohexane. Again, this is a 3D plot of electron density around that molecule. Very difficult to understand. Interestingly enough, which is why I've used this in the talk, right? This is a topological spine of the electron density. And it's not an accident, right? That happens to look almost exactly like the chemical drawing, right? Because that's just what happens, right? The hydrogens are much closer to the carbons, and the carbons have a lower saddle. So if you look at the topology of the density, it just happens to look exactly like its chemical graph, right? But you can do this in arbitrary dimension. This is one of the standard optimization functions that people use. It's called Ackley's function. People use it to test optimization algorithms. And you can look at its structure in 2D. You can look at it in 3D, in 4D, and 7D. And I mean, yeah, 7D, it's hard to understand, but you totally see, right, the recursive nature of the way this thing is defined. And at least you have a way to understand how many local maxima they are, right? How they're connected, that there's this hierarchical nested structure in this function. And you can do that in arbitrary dimension, which is like would be fairly impossible with any other technique, I would contend. And you can do this in the example before, right? So this is actually the topological spine of the very first example that we saw, right? So we see these two large maxima of yield. One is the big red mountain that we saw before, and the other one is the smaller blue mountain that actually shows you the relationship here. And we in fact have tools called NDAF that allow you to connect all this in kind of an interactive visualization system where you've got a scatter plot and you've got the topological spine and you've got a parallel coordinate plot, and you can click on one or the other, do a selection, understand kind of what's the scatter plot just related to certain local maxima and so on. So that essentially is a very generic way of understanding high dimensional topology. I'm going to go skip out of that. The rest of this was essentially doing viewpoint selection. Let me skip out of that and then do another version with more relevant examples that we did more recently, where we're actually using the same kind of structure, not necessarily to understand something kind of in principle scientifically related, right? I no longer am trying to understand yield, but in this case, I'm actually trying to understand the machine learning model itself, the training process. We'll see how that works kind of with similar tools, right? So I'm sure, right, everybody is aware right now that we've transitioned into, right, the brand new world of machine learning and data-driven models, where we just throw some arbitrary amount of data that we've collected or simulations that we've done, right, either in NIF or the middle one is the cancer biology problem or in additive manufacturing, and try to learn a model, right? The computer will train a model that supposedly is going to go solve world peace. Okay, so the way that works, right? That's a fairly similar example. Just a couple years later, from the NIF, they actually created 100 million different simulations in a 5-dimensional parameter space that were predicting things like X-ray images and various scalar outputs and spectra and a whole bunch of other kind of virtual diagnostics of the NIF target capsule. And they trained a model, right? They trained a machine learning model to kind of do this prediction, build a surrogate, do the optimization. But that's a very difficult process, and also a very unintuitive one, right? You stick all that data into like a TensorFlow system, you wait for a couple hours, and out falls a model that does something. How do you know that that model is correct? How do you know how well it fitted? Did that thing even converge, right? So we have all these questions about, well, how well did that thing actually fit? And typically what we do is plot like these, right? They're called, right? So you've got the loss function, so some metric of goodness of fit. And then you look at the red curve, which is what happened during your training. You've got a holdout sample, right? The typical cross-validation, which is the blue sample. You look at those two curves, they kind of seem to converge, right? They make a plateau, and you go like, yeah, that kind of worked, right? That model fit did seem to converge, so I trust that. But that may not be the right version, right? So you have other questions. So maybe this model worked reasonably well overall, but maybe there's a small region in parameter space where it didn't work at all. We wouldn't see that here, right? This is kind of an L2 average metric. So we want to know where it worked and where it didn't work, right? Where is it harder? Where is it neither? So we need to understand this high dimensional function, but just like that high dimensional error landscape. We want to know, are there regions where it's better or regions where it's worse, regions where it's more complex? And we can just treat that just like what we just saw with scientific data, right? We can treat it as a high dimensional function. It just happens to be, we've got a bunch of input parameters, and we've got the error at each function, and that tells us what the function is that we are interested in analyzing. So we can do similar things with traditional approaches, right? So here's a parallel coordinate plot. These are so each of these coordinates, for those people who are not familiar, right? Each of these lines is essentially one coordinate. So that we've got 5 inputs, and then, right, the total yield and the total error is the output. It's always the last one here. And now every line in here is essentially an input-output sample, right? So every line has 5 input parameters and then 1 output. If you look at the total error, doesn't tell you much, right? So most error is really low. That's good. Seems to be some structure. We don't quite know what. Forward error, right? This is just the model of the forward prediction error, subselected around some really high errors. There does seem to be something going on, right? So most of the points are in this input parameters over here, but there's a couple of ones that give you a high error that are here. It's not quite clear what that means. I can look at the scatter plot of something similar, right? So this is, I don't know, this is one of the shape parameters, one of the input parameters versus the error. You don't really see a thing because, right, 100 million points in a scatter plot doesn't really work. So, right, I can do those plots. It's not quite clear what they tell me. So again, let's go back to topological spines. I'm going to skip through that a little bit faster because we've kind of seen this already, but it might bear to look at, right? So again, we've got this idea that we do the high dimensional function, we extract the local extrema and the saddle points, we make this 2D terrain metaphor, and then we get to something like this, right? So where essentially this parallel coordinate plot of total error actually resolves to this topological spine that immediately tells you there's actually two regions that get you a very high error, right? And in fact, then you can look at just the forward error, and you see that there's actually more structure in there. There's actually, what is it? 1, 2, 3, 4, 5, 6, 7. There's 8 different local maxima that all have a very high error, right? But are locally distinct. And again, right, the sizes of these actually indicate the number of points that are part of it, right? So this maximum has a lot more points than that guy, right? Or a lot more points than this guy. So there's some isolated places where there's a high error and mostly things are low error. So we saw that, right? We've got this nesting contour. We end up with the contour plot like this. We also end up with the actual segmentation, right? So that's something that we didn't really concentrate on before, but this is the same Morse complex segmentation that I showed in the other slide, just kind of superimposed on the contours. And here, what this means is that we can restrict whatever statistics we want to specific regions in this topological spine, right? So we can ask, what's the scatter plot just for these points or just for these points? And we saw that can be useful, right? That's the coloring that we saw before. So let's see, where are we at? So 9:35. So these are some of the computer science. I don't know how much interest it is, but since the slides are here and we have some time, I might as well go over it. So there's some interesting, challenging computer science problem here where if you actually want to compute the topology at this size, normally, right, we said, right, we take all the points and when we have to compute this graph and then using the graph, we compute the topology. Well, okay, so we have 100 million points in 5D space. You just kind of rough estimate, right? It's going to end up being about 35 edges per points. So if you've got a random distribution of points, that's just the number of kind of nearest neighbor that you end up with. That gets you 3.5 billion edges, minimally encoded. That's 13 gigabytes just of raw binary data. So that just doesn't, right? That doesn't work anymore. So what we figured out here, and that we can do it in kind of a streaming construction because the points themselves are not that large, right? Because it's 100 million points, which is big, but it's not super large. It's the edges that really kind of kill you here. And you can do this in a streaming construction. So we think about like all our points, and what we're going to do is essentially for each point, what we need to know is the steepest line to its neighbor, right? Because that's how the segmentation is defined. How do I know which maximum I belong to? Well, I take the steepest line until I reach my local max, and that tells me, right, which is my maximum. So I really need to know what's my steepest neighbor. And so I can just, right, do some local KD lookup structure, stream through the points, and for every point, I find my nearest neighbors. And then for all of those, I compute, right, the steepest line, and then I get the next guy, and I just keep updating on the right. I just keep updating, right, the steepest line based on all the edges that I've seen. And so once I'm done with all of that, I get kind of this connected structure where, right, I get a segmentation into already mountains, right? So each of these guys is a rooted tree where the root essentially is the local maximum because that's the one guy that has no outgoing edge, and everybody else kind of feeds in there. So I can, right? So then I can just do a union find, and that identifies the local maxima. Now, the one annoying part here is that that's a single pass algorithm that identifies 99% of the information that you want, right? You now know where all the local maxes are, you know how tall they are, you know the segmentation into local maximas. What you don't know anymore is the saddles that connect them, right? You don't know how these mountains are locally connected because that line is not the steepest line, so it got thrown away in the process. So unfortunately, you have to do the whole thing again. You do another streaming pass to kind of identify these extra gray edges here that are kind of the second steepest line out of the saddle, or the steepest line that connects you to the next mountain. And then you can do the same thing, right? You can start simplifying the mountains, right? I can merge the blue one with the yellow one, which, right, creates the same cancellation tree as we saw before. Again, this is available on GitHub, right? So this is another view, a later view of the same tool, right? Where you've got the parallel coordinate plot on the top, the spines on the bottom. You see how they are linked. So I can select things in the scalar plot, and then the topological spine kind of tells me where those points are, and kind of in space of this abstract notion of the topological spine. I see the scatter plot adjusting. Right, so this is fully interactive. Oops, I get out of here. I want to see that again. And that actually now allows us to understand kind of our error landscape a little bit better, right? So we saw that we have these two peaks of the overall error. These are the input parameters. And then if you look at these two peaks, it turns out, right, they really separate one of the shape modes, which turns out to be symmetric. So what you end up saying is there's a really high error in this model if the implosion essentially makes this very symmetric leaf-shaped structure, and essentially there's a dual structure that's slightly rotated that has the shape number can either be negative or positive in this case, and it creates kind of the same error. I can also look at what actually creates the different pieces of the error. I didn't have time to go through this. This is a particular submodule of the model that we are creating. Again, the spine tells you that there's two independent ways of creating really high error. And again, one of them, right, the high one turns out to be the very complicated structure, and the stuff that's really low is kind of a very simplistic shape that doesn't have these things. I can look at the forward error. I can now look at individual points. So I can look at the local maxes of this function, and then start looking at what actually happens. And it turns out that that is probably what we found here is simulation artifacts. So some of these local maxes are very few points, sometimes even single points, that make these maxes among the 100 million that we've analyzed. And if you look at the actual images that correspond to them, you see these weird ring artifacts around the image. I don't know how well that comes across in Zoom, which obviously confuse the models, but are also probably not physics related, but are some high frequency noise pattern that is probably an artifact. We can also now compare things over time. So the top model was after 40 epochs, so after a certain amount of training of the model. The bottom one, we just doubled the training data, the training time to 80 epochs. And it turns out that these modes actually disappear. So at some point, the model starts learning these high frequency patterns, even though they're probably artifacts, but the model can learn them, right? And then your topological landscape becomes a lot simpler because these artifacts are going away. So ultimately, what we have is that if we can use this new streaming algorithm, or it's new at the time, right, we can construct high dimensional Morse complexes of very high dimensional functions, very large number of points, which then allow us to do this linked exploration and visualization of high dimensional functions. And that kind of helps us to understand both kind of scientific data, as we saw in the last talk, right? We can actually understand where there's a high yield and where there's a low yield, but it also allows us to understand the model itself, right? Where is the error high, where's the error low? We've done the same thing for some cancer moonshot data where we had simulations of proteins on human membranes, and they were sampling in high dimensional spaces there as well. And all this is available kind of as an interactive tool. So ultimately, right, what we have done is we can get you from just looking at single loss curves where you just know on average this thing works kind of well, to, right, a much more intuitive, interactive, and much more local analysis of these high dimensional functions that tell you a lot more about exactly what your error function is doing, or exactly what your physics is doing in your high dimension parameter space. So that is all I had for today. And I'm happy to go explain any of this in more detail, or find some other pictures to help people with these concepts. And I know that it wasn't very well structured based on the last minute.
No, thanks, Timo. It was great. It was really good. So yeah, I can start with one question. So this topological analysis basically lets you also uncover patterns that may be not clearly visible, but can be used also for anomaly detection in a sense in your data or in your models. Would that be the purpose? Yeah,
and in fact, we in some sense that is what this is, right? It's an anomaly detection. So a lot of times it's, as long as the anomaly represents itself in your output function, then you will absolutely see this. You will see these weird spikes in your data that create like let's say very high value maxima at a certain place in your parameter space. And then you look at those maxima and you go like, oh, yeah, that was just weird, right? So we've had other data from NIF where they had fitted individual models, or different models, not deep learning models, but other statistical models to their simulation data, and they had similar artifacts, right? They would find very smooth functions everywhere, and then there's like one place where your function is 2 orders of magnitude higher, and it turns out that those are probably most likely artifacts.
Mm-hmm.
So yeah, it can definitely be an outlier detection as long as the outlier is kind of represented in the function that you're analyzing, right? All of this depends on understanding the like a certain function. So if I have a function that is meaningful, then this is very useful.
Gotcha. So we have a couple of questions coming in also on Discord. I will relay them to you.
Sure.
So could you explain more what streaming computation means?
Oh, so instead of creating the graph and hold it in memory, so instead of constructing it and having to store it, what I'm going to do is I'm going to just take the points in some arbitrary order, and I can hold the points in memory, so that's not a problem, right? So you go back here. So 100 million points on a modern computer is not that big of a deal, but like 3.5 billion edges is. So what I'm going to do is I'm going to go through these points, what we call streaming order. So I just take one point, I construct its edges, I compute which of those might be the steepest one, given on all the other ones I've seen. But then I throw the edges on the left, I throw them away, right? I don't store them. So then I just go to the next guy, I'm constructing a next set of edges. I'm going to integrate them into kind of the set of steepest edges on the right. And again, I'm going to throw the edges on the left away. So in that sense, I go through the same graph. In fact, I go through the graph twice because every edge is typically constructed twice, once from both sides. So I'm actually going to go through like 7 billion edges, but I'm going through them, always throwing them away as soon as I've computed from them. So then I don't have to store them. And that means on the right, I only have to store 1 edge per point at most, because each point only stores its steepest edge, rather than each point storing like 35 of its neighbors. And so that way I can actually compute this with a very large number of points, which otherwise I would have needed a very big machine to do it.
And if you could talk more about the computational complexity of these topological and graph-based algorithms, that was a follow-up.
So the algorithm that beats the topology, right? If you think about what you end up doing is, so this complexity is O of the number of edges, right? I need to look at every edge and decide whether it's steepest. And then I need to go kind of from the graph to the colored graph. And that is just a union find. So that's amortized O of n, because I can shortcut everything, right? Once I have the steepest line, I can start anywhere. I will just jump through this until I find the max. But then, right, everything on this path has already been solved, so they don't need to look at it again. So that for those familiar with that, that is a version of just the standard union find, which is O of n. What is it, n times alpha or something, or alpha of n something. So something just ever so slightly above O of n. So this is dominated by the complexity of creating the graph. And that strongly depends on what graph you want to construct. I have a different, I could have given a different talk on just how to construct these graphs. If you think about something like a nearest neighbor graph, so KNN graph, which many people do, it is kind of sort of O n log n in the number of points, because you build a KD tree, and then for each vertex, you just ask that KD tree about the nearest K edges. But there are more complicated constructions that get more expensive. So it's manageable. Also, in a lot of cases that we practically see is that there's very few people who have the wherewithal to compute 100 million simulations. It's quite the opposite, right? Typically, people struggle with computing 1,000 simulations. So the data size of the graph has rarely been an issue. It's just kind of working with a little more that actually becomes a thing. I should draw this here so I look at people.
Okay, I think, yeah, the participants are thanking you also for the reply to the questions. And we have a request if you could post the URL for the web interface that you showed.
Yes, let me, so it's, where do I have that? So it's called NDAV, N-Dimensional Data Analysis and Visualization. Whoa. I thought I had it on, didn't I have it on some slide? Maybe not. But if you literally do, you just look for NDAV Bremer. Oh. Yeah. So if you do NDDAV, N-Dimensional Data Analysis and Viz, you'll see a GitHub.
Okay.
And I don't, yeah, so obviously this is a prototype code. Shusen is still working with us, so there's a lot of changes, so it might look different from what you saw on the slide. But on the other hand, this is now fully integrated with Jupyter notebooks, so it should be easier to install. So you can just look for LNNL and then NDAV.
Great. Yeah, great. We got some excitement because NDAV is in Python. Okay.
Yes, there's a little bit of C++ under the hood, but hopefully
right.
you shouldn't need to see that.
So you can run it locally, or do you usually use, you know?
Okay. Yeah, you can just run it locally. You can pre-compute things, and also it depends a little bit on how big of a graph you want to make. You can just, if you have small enough graphs, you can just do it on the fly. For larger things, you need some pre-processing, but yeah, hopefully that's useful. If not, we can try to help out.
Awesome. Do we have any more questions for Timo? I think that was it. I don't know, Paul, did you have any questions or?
Not really. I was just following the Discord discussion. No, thank you for, well, maybe I did have a question. So with when you look through, you make a database of information. In the field I work in wave propagation, oftentimes, you know, some of our problems, we have missing physics. There's some missing physics. And as I followed your presentation, it seemed to me some of these, what do you call them?
Topological.
Pardon?
No, go ahead. Sorry.
Yeah, could that be an indication of missing physics?
I mean, not directly, but what we in fact are doing right now, as in like I got an email this morning, is you can totally use it to compare two different physics packages, for example, right? Or if you have enough data, you can compare your experimental data with your simulation data in this topological motion. And that can actually then tell you about, right, some missing physics or some differences. Right?
Yeah,
so
could maybe tell, you could look at where these discrepancies or discontinuities happen. Maybe there's some common feature.
Yes.
About
and
them.
also the difference is, of course, that you can do that now, right? I mean, if I give you two databases, right, one from the experiment and one from the simulation, you can of course compare them, right? That's not hard. But what this gives you is that it tells you something about where those differences are and how they're kind of organized in space, right?
Yes.
Is there a particular region in input space where this happens, or are you just generally off, right? I mean, is your thing just offset, or is there an extra mountain that appeared, right? Is there another mode in your function that the simulation didn't capture or something like that, right? So we're actually literally doing that right now with some of the NIF simulation, where they have something where they analyze things with fuel in the NIF cup so that can actually ignite, and then fuel that can't, like burn on and burn off, they call it. And then the question is, okay, where's the difference, right? What's the, right, where in space does it react different? And that then becomes really interesting. So again, this knows nothing about physics, but if you want to compare things, that can be very powerful.
For example, on a database of simulations, we might often see some anomalous features, okay, that aren't in the experiment, like waves damp way off axis, and they just don't in the experiment. And it's useful, it could be very useful to look at if there's a characteristic set of input parameters that characterize that part of,
yeah,
which might lead you then to some conclusion or guess about what missing physics you have.
Yeah, absolutely. Yeah, that's the perfect use case. And also, I mean, like comparing the actual true simulation with some surrogate model of it, or comparing a 1D simulation to a 2D simulation, right? Or generically, right, a low fidelity version against the high fidelity version, right? All those things become, I would claim anyway, more intuitive.
So you just brought up something. It's a very interesting thing. In our field, we try to make model hierarchies for different things. In wave propagation, for example, you might have ray tracing and then a 2D, two-dimensional full wave, 3D full wave. And it's very important to try to distinguish where the overlap regions are, where the models are valid and where you should go on to your next model in physics fidelity. It would be very useful to characterize those differences this way.
Yeah.
We have an additional question on Discord. What other approaches to high dimensional data analysis do you find useful in your work?
Sorry, say again. So which high dimensional?
So what other approaches to high dimensional data analysis do you find useful in your work? I guess beyond the ones you showed.
I'm obviously fully objective here, so I'm partial to a lot of stuff that is related to topological analysis, because I'm attracted to the analyze first, project later approach. We have also done things about just optimizing projections, finding better viewpoints, right? So this idea that, yeah, I mean, I have no illusions of how intuitive these topological spines are to people, right, other than myself, because I've tried explaining it to other application folks in biology, and even after several rounds of this, they're all like, yeah, I don't quite understand it. So then we went like, well, okay, so if people are really just in tune to 2D scatter plots, then what is the best 2D scatter plot that you can make? And it turns out you can certainly make better ones than just like looking at arbitrary combinations of your input parameters. So there's other work that I think could be very useful because it stays more within traditional metaphors of looking at things. But I mean, doing what I'm doing, I am very partial to a lot of the topological analysis, and there's many other people that are doing related things and have been doing. There's a whole high dimensional analysis community on the computational geometry front and topology people, because it allows you to look at the structure first and then kind of understand what that structure might mean, versus having to first kind of project things into low dimensions, which might destroy everything that you were looking for. It might now be gone in a projection artifact, and then you wonder why don't you see any meaningful patterns in your data right after the projection, which is also similar. I have similar concerns a lot of times. Like nowadays, people do like TSNEs or other like non-linear high dimensional dimension reduction to get these plots. And it's always a little bit funky to me because you don't know what that system did. It's very hard to kind of intuit what you are now looking at, versus, right, however abstract topology might be, at least I know exactly mathematically what I did and what I'm looking at, which is very different from kind of a non-linear high dimensional data reduction. Sorry, that was a very long-winded answer.
No, that you made perfect examples. Thanks. Okay, so I guess if we don't have any other questions, I'll give it a second here on Discord. I don't see any. I think you got appreciation for your talk and definitely on our side for putting it together in such short notice, like you know, a second before. And yeah, thank you, Timo, for being our
I'm glad
guest
that was useful. Thanks a
school.
lot. Those were good questions. And yeah, if anybody has more questions, write us an email or something. We're always here.
Yeah,